Everyone, my name is Culp Drew, and today I'm going to be presenting my Lab 5, which is going to be discussing Faraday's Law. So in this lab, the purpose was to collect observational data of a magnet falling through a conductive tube of aluminum foil, and we're going to be modeling the magnet and tube interaction using a computational model through GlowScript. So the physical model was the magnet and tube of aluminum, and this is simulating the induced current. So we expected our results to be that if we had higher mu values, which we got from lab 3, that will result in more extreme ranges in the results. So some important concepts. First, magnetic field of a bar magnet. We're going to be looking at the B field of a dipole as well as the Biot-Savart law and its applications. Another really important concept that we'll be seeing in this lab is Faraday's law, as well as some applications of Ohm's law, the magnetic force on a falling magnet. This is going to help us derive some of our values and help us with our calculations. Lenz's law, the momentum principle, and Newton's third law, as well as Newton's second law, and superposition. So these were the initial conditions of the magnet and the tube. As we can see, the magnet had a mass of 0.022 kilograms, and this would, of course, vary depending on the magnet used from person to person. The length of the aluminum tube and the dimensions like the width and inner radius as well as the total radius were also found, and the mu value was 2.15, and this was derived in lab 3. So this is just the code snippet that represents the dipole formula. So we're going to be using the formula to calculate the flux, and that will help us with the next portion of the code, which is calculating the magnetic force and also the relative velocity and the position, which will be an application of Newton's second law as well. And so our computational model that was generated resulted in the graph on the right, as well as the time in the tube being 10.93 seconds. So the magnet was in the tube for 10.93 seconds, which in the real world model seems a little bit unrealistic, but in the computational model, based on the given values as well as the mu value, it was calculated to be 10.93 seconds. So the clockwise flow was indicated by the red color current, and the counterclockwise flow was represented by the blue color current. The counterclockwise direction is shown by the resistance against the increase in magnetic flux. And if we flip the magnet, the direction of it falling would still be in the negative y direction, the same direction. Since this is the opposite direction, there would be a result in there would be a resulting decrease in flux, and so the flux would decrease because it's going in the opposite way. And the real world system would be more accurate if we were to model this experiment, since the computational model may take into account more errors, such as like a miscalculation of the mu value, which, as I previously mentioned, could cause the time to be higher in the calculations. The shape of the velocity versus time plot also tells us that the net forces acting on the bar magnet will all sum to 0. So there's a 0 net force while they are inside the tube, and this indicates that there's equal and opposite forces. So the what if questions included the resistivity of the conductor and how would the net dynamics of the magnet that was falling would change based on the resistivity being reduced. So the magnet would in turn take longer to fall, and the current would have to end up being larger. And this is if the resistivity was reduced as close as possible to 0. And the next question was, what if holes or slots were cut into the tube, and how would this affect the ring currents in the model? And both the magnetic force and the induced current would decrease, and this would result in the speed at which the magnet is dropping to be increased. And that is it for my Lab 5. Thank you so much for watching.